अस्सलाम वालेकुम। आज के लेक्चर में हम डिस्कस करेंगे बाउंड्री लेयर assumption, mass flux, momentum integral equation, flow with zero pressure gradient, use of momentum integral equation in laminar flow। इससे पहले हमने बाउंड्री लेयर और रेनॉल्ड नंबर के बारे में पढ़ा था। बाउंड्री लेयर की भी इक्वेशंस हमने डिराइव की थी। तो सबसे पहले ये हमारे पास जो बाउंड्री लेयर इक्वेशंस हैं वो हमारे पास लैमिनर या टर्बुलेंट फ्लो से रिलेटेड बनती है। तो जब आप इन चीज़ों को डिस्कस करेंगे और एनालिसिस करेंगे तो बाउंड्री लेयर डेवलपमेंट आपके पास बनेगी u इज इक्वल टू यू एट वाई इज इक्वल टू डेल्टा एंड विद डेरिवेटिव एंड विद द कंडीशन ऑफ बाउंड्री लेयर। ये विद इन बाउंड्री लेयर आपके पास क्या कंडीशन हो, या थिन कंपेयर है या आपके पास उसकी लेंथ कैसे है, तो इन सब के पैरामीटर यूज़ करते हुए प्रेशर ग्रेडियंट का पैरामीटर यूज़ करेंगे। अगर हम प्रेशर वेरिएशन अक्रॉस द थिन बाउंड्री लेयर लें तो वो आपके पास निग्लिजिबल होगा। अगर फ्री स्ट्रीम प्रेशर की बात की जाए तो वो हमारे पास बाउंड्री लेयर में एग्जिस्ट करेगा। थर्ड हमारे पास अब कंसीडर करते हैं इनकम्प्रेसिबल पैरामीटर के स्टडी हो, मीन्स के विद रिस्पेक्ट टू टाइम इसकी कांस्टेंट है। टू डायमेंशनल फ्लो ओवर अ सॉलिड सरफेस, द बाउंड्री लेयर थिकनेस डेल्टा ग्रोज in some other manner with increasing distance x. Here is the geometrical representation of the flow in the channel, like there is a two-dimensional flow in increasing distance x. For our analysis we choose a different control volume for the length dx with w and height delta x, which you have seen in the figure. Free stream velocity, and we wish to determine the boundary layer thickness delta as a function of x. There will be a mass flow across surface AB and CD, means you have to deduct the channel into two parts like AB or CD. Here is two sections AB and CD. At both sections you will determine the boundary layer and differential control volume about ABCD. What about the surface BC? Surface BC is not a streamline. It is the imaginary boundary that separates the viscous. Here is another parameter in this equation. Viscosity. What is the viscosity? Related to density and the flow across the volume surface BC. What is the mass flux? Mass flux, since control surface is adjacent to solid boundary, there will be no flow across and before considering the force acting on the control volume and the momentum fluxes through the control surface. Let's apply the continuity equation to determine the mass flux through the each portion of the control surface. Here is some assumption and two-dimensional steady flow. For basic equation of the continuity we have applied to steady flow and two-dimensional flow. Let's calculate the width by using the mass flux through the AB surface. CD is located at x plus dx, expanding m in a Taylor series. The arrangement about the continuity equation after momentum fluxes and force associated with control volume ABCD, these are related to the momentum equation, and rearrange all the equations in simplest way we can find. Here Fm represents the x component of mass flux, momentum flux. To apply this equation to the differential control volume, so there is another x momentum flux through the control surface and also the surface force acting on the control volume in the x direction too. Let's consider the mass flux first and again consider each segment of the control surface. Momentum flux, here is another momentum flux at the cross section area of AB at x. Since the flow is two-dimensional and the momentum flux AB is given as according to the last equation. Here is CD is located at x plus d, so there is the mass flux according to the CD x plus dx with the momentum flux equation. Now rearrange the equation in the x direction, and momentum flow across BC is given by MFBC is equal to UMBC. Now calculating all the equations, so now that we have a suitable expression of x. Momentum flux through the control surface. Let's consider the surface forces acting on the control volume in the x direction. Note that the surface AB, BC and CD all experiences formal forces like pressure or gravity or something else that generate the forces in the x direction. In the addition, shear forces acts on surface AD. Since the definition of the boundary layer, the velocity gradient goes to the zero at the edge of the boundary layer. Here is the geometrical representation for the differential control volume. For the surface forces, you can say if the pressure is at x is P, then the force acting on the AB is given as F of AB is equal to PW delta. The x component of the normal force acting over BC is given as like this, and the average shear forces acting on AD is given by in this form. Now summarize all the x component according to the forces and in the x direction of the control volume, so that you can say that delta x delta dx d delta is less or equal to delta L, like ta. So neglect the second and fourth terms of the equation. You can write the equation in this form, and that one is the summarized form of the surface forces. Equation above is a momentum integral equation that gives a relation between x component of the forces in the boundary layer and the x momentum flux. The pressure gradient dP over dx can be determined by applying the Bernoulli equation to the inviscid flow. For the viscid flow, you can use the continuity equation, but now we have inviscid flow, then you can use the Bernoulli equation flow outside the boundary layer. Is the representation of the momentum flux with inviscid flow and using the Bernoulli equation. Using the definition of the displacement delta and momentum thickness theta, here is the equation of the momentum integral equation. This equation which yield an ordinary differential equation for the boundary layer thickness as a function of x. With zero pressure gradient, laminar flow, if we have the laminar flow, what we have for the reasonable assumption for the velocity for profile at polynomial 1 in y, you can write the laminar flow in over a flat plate u is equal to a plus by plus cy square. Like this physical boundary condition here are at y is equal to 0, u is equal to 0, y is equal to delta, u is equal to capital U, y is equal to delta, and partial u or partial y is equal to 0. Evaluating the constants A, B, C given as that, in this form you can write the laminar flow over a plate. Note that the thickness and numerical value of the integral in equation is given as in this form, so you can write the summarized form of the equation, obtaining the expression for the T delta in terms of delta. This will then permits us to solve for delta of x. Substituting the assumed velocity profile, now the expression of tau w can be written as in this form, and the momentum integral equation, and substituting the value of the tau w. After that, you can find the momentum equation. Delta over x is equal to square root 30 mu over rho u x is equal to 5.48 over our Reynolds number. Equation shows that the ratio of the laminar boundary layer thickness to distance along a flat plate varies inversely with the square root of the Reynolds number. It has same form as the exact solution derived from the complete differential equation of the motion by Blasey's like a Bernoulli equation in 1908. Thank you so much.